Good morning, everyone. In the last class, we have discussed about the stability issues with respect to any transfer functions. Now, say for example, a system is given like this. Here, we will actually discuss the Routh Hurwitz stability analysis criteria. Routh Hurwitz stability analysis. How the stability analysis is performed. For example, GS uh, is given like the system is given like this. For example, this is your RS, you see, this is your CS, and unity feedback control system is there. And for example, GS is given at 2y s into s plus 4. So what is your overall transfer function? That means CS by RS will be equal to GS by 1 plus GS HS. That means this is your open loop transfer function and this is your closed loop transfer functions. When the system is made unity feedback, that means you have to consider the closed loop transfer functions, right? So closed loop transfer functions is like this: 2y s into s plus 4 by 1 plus 2y s into s plus 4. So if you solve it, you get s squared plus 4s plus 2. Now, what is this? This is a second order system, right? So how can you get the stability of it? First of all, you have to get the poles. So in order to get the poles, what you have to consider? You have to consider denominator part. So denominator part is generalized term, that is 1 plus gs into hs. If you just tally these two part, what you get? You get 1 plus gs into hs equal to s squared plus 4s plus 2. And in order to get the poles, or what are roots, basically what you have to do, you have to make s square plus 4s plus 2 equal to 0. That means in general case we can say it 1 plus gshs equal to 0, right? So this is known as qs, or characteristic equation. So in order to get the poles or roots of any system, that means to get the stability, you need to find out the characteristic equations first of all. So characteristic equation we get s square plus 4s plus 2. See, so s square plus 4s plus 2 equal to 0, right? If you solve it, you get by Sridhar Acharya, what you get? Minus 4 plus minus root over 4 square 16 minus 8 4ac by 2. So get minus 4 plus minus root over 8 by 2. That means minus 2 plus minus root 2. So one pole is at s is equal to minus 2 plus root 2, and one pole is at minus 2 minus root 2. That means this system is second order. That means you can find out the pole locations, and in both the cases you see this is having the negative real roots. So the poles are lying on the just left hand side of the system. So if the poles are lying on the left hand side of the system, what you will get? System is closed loop stable, right? You get the system is closed loop stable. That means once you can get the roots calculated from any system given to you, that is from the characteristic equations, if you can find out the roots easily, then there is no problem. But see, the system is such that this order may be 4, maybe 5, maybe 6, maybe 7, because during your block diagram reduction technique you have seen there are several number of blocks which are interconnected together, and if say for example 3 systems are cascadedly connected and each of the system is having second order characteristics, then total you see 6th order system will be getting, right? If the system is of 6th order, so I don't know, or the scientists have not found any system how you can find out the roots. Okay, So if you cannot find out the roots, you cannot place the poles in the S-plane. So if the system is the poles cannot be placed in the system this S-plane, so according to the rules we know, either left hand side rule or right hand side rule or imaginary axis, on the imaginary axis rule, we cannot find out the stability of the system. That means the problem is there when the system order is actually increasing, right? So if the system order is increasing, so how in that case you can find out the system stability? So that is the problem. So problem was with actually system order. That means if the system order increases above 3 or 4, up to 2, so no problem. Above 3 and 4, the solution is difficult. Solution is not possible. So in that case, what you have to go for? You have to go for to take help the formula or the calculations made by scientist Routh Hurwitz, and they have what they have done that they have actually used an array. They have used an array. That array is known as Routh array, and the criteria is known as Routh Hurwitz criteria. Okay, so let us now concentrate on Routh formation of the Routh array. So formation of Routh array. How Routh array is formed? So with the help of polynomial, that means characteristic equations. First of all, we have to consider the characteristic equation QS for any system given to you. Okay, that means if the system open loop transfer function is given to you, you have to get 1 plus GSH is equal to 0. From that you get the characteristic equations. Maybe characteristic equation I may write it like a1 is n minus 1, a2 is minus 2, so on, an equal to 0. I have just written a nth order polynomial, right? This is nth order system. It may be n is equal to 2 second order, n is equal to 3 third order, n is equal to 4 fourth order, n is equal to 5 fifth order, and like this. That means this is your characteristic equation or characteristic polynomial. First of all, say for example, if this is your nth order, then this a0 must have to be positive, right? The conditions, first conditions, when the Routh array can be formed, if the a0 is positive, that means the coefficient of highest power of s in the characteristic equations is to be positive. So coefficient, we may write it like coefficient of the highest power of s in characteristic equation must be positive. If this condition is satisfied, then we may go for the formation of the Routh array, right? So we are not generalizing it. We are going to get one example how this from these characteristic equations given to you, you can actually get the Routh array, completed Routh array, and from Routh array, after completion of the Routh array, we will consider how to get the stability from it. Okay. See, we are considering a fourth order characteristic equation of our one system. That means if the characteristic equation is given to you, so Qs is equal to s to the power 4 plus 8s cube plus 18s square plus 16s plus 5 is equal to 0. So this is the fourth order characteristic equations. Now how to find out the Routh array? So formation of Routh array, we will just consider. So this highest power is 4, so its coefficient is positive 1, right? So what we have to take, as this is one array, so we will consider the highest power of s in the denominator, s to the power 4. Next we will write s to the power cube and so on, s square, s to the power 1 and s to the power 0. That means we will have to form an array with these coefficients of s to the power 4, s to the power cube, s square, s to the power 1, s to the power 0. If the order is of fifth that is fifth order characteristic equation is given to you, then this will be s to the power 5, s to the power 4, s to the power cube, s to the power 2, s to the power 1, s to the power 0. If this is a sixth order, so s to the power 6, 5, s to the power 3, s to the power 2, s to the power 1, and so on up to s to the power 0. Right? Once you write this, next, what you have to take? You have to take the coefficient of s to the power 4. What is the coefficient of s to the power 4 here? This is 1 plus 1, right? And what we will consider the next elements is just one element after this. Then skip one element in between. Say, for example, if this s to the power 4 is given to you, then you have to skip s to the power 3 terms, and rest of the term you have to next term you have to take. That means coefficient of s to the power 2, that is 18. Right? Next, what you have to take? You have to take one coefficient which is just skipping one term in between. That means after s to the power 2, you have to consider this term s to the power 0. That means this value will be 5. Right? So this is the construction of the first row of this completed array. Next next you have to consider this row s to the power cube. Now when you will consider s to the power cube, this is your coefficient 8. Next, by the same procedure, what you have to do? S to the power cube, you skip s to the power square term, and next term is s to the power 1. So 1 after 1. Actually you have to skip 1 power of s in between. That means you are taking the next step 8, and this will be your 16. And is there any term? No, this is 0, because all the array must be symmetrical. So if there is 3 elements, so there will be also 3 elements, and in all these 3 on this rest of the 3 arrays rows, you will find 3 elements in each, right? So that is the initial formation. That means first 2 rows of the Routh array will be formed. First 2 rows. So first, these are the first 2 rows are formed by given polynomial. So given polynomial, from the given polynomial, you have to find out the first 2 rows. Once these 2 rows have been formed, next automatically you can get the rest of the rows. How the rest of the rows are formed? I will just give you the red line. I see this is the first operation. Red means first operation. Okay. Red lines means the first operations, and black line I will consider for the second operations. Black for second operation. Right? Second operation means what? I will see 8 into this third element. That means onwards all the elements will be formed with the help of the mathematical analysis. That means 8 into 18. This is your first operation, minus second operation. This is your second operation, 1 into 60. Right? So first operation means this 8 and this 18 is multiplied, minus second operation. Second operation is denoted by black. So this is 1 into 16 divided by this first element of the previous, first element of the previous row, first element of the previous row. So division by first element of previous row. Okay. So this will give you some value, maybe equal to, I can give you as is 16. Right? So you have to form the next element. Next element is formed by the same system. What is the system? This 8 is multiplied with the 5. So next element will be formed like 8 into 5 minus you get 1 into 0. This is your next operations. So 1 into 0 by the first element again. So all the elements which will be found in this row, in each case you have to divide the numerator by the first element of the previous row, that means by 8. So this will give you actually 5. So you get 2 elements and there are no elements, so definitely this will be your 0. So in the previous row, what you have obtained, this is that is the coefficient of s square, you get 16, 5 and 0, right? So once s square row is formed, next you have to form the coefficient, there is a row consisting of s to the power 1. How it can be formed? You see, with the same procedure, what you have to do, you have to take this element and this element, previous 2 rows. See, when you have constructed this s to the power 2 elements, you have considered the previous 2 elements. So these are the previous two rows. So when you consider s to the power 1, you have to consider these 2 rows. These 2 rows you have to consider. So elements are like 8, 16 and 0 and 16, 5, 0. So what you have to do, you have to just consider the same procedure. That means 16 into 16 minus, you can say 8 into 5 divided by 16, because what happens here, you see, in every case the last element, first element of the last row will be the element which will be considered in the denominator. So you get 16 into 16 minus 8 into 5 divided by 16, because 16 is the first element of the last row. So this will give you some value which is say 27 by 2. And you see, if you just multiply this term, next how to get the next, this is 16 into 0 minus 8 into 0. So 16 into 0, next this into this, okay, and this into this, so minus 8 into 0 by 16. So this will be 0 and this is 0, okay. So this is the formation of your s to the power 1. So when you formulate this coefficient or of this array, that is this row, we have to consider the last 2 rows, s2 and s1, and the elements are like 27 by 2 into 5. So how, this is your first action. So 27 by 2 into 5 minus 16 into 0, you see, by 27 by 2, because this is your last previous row first element, and this is 0 and this is 0. So what you will get, this is equal to 5, right? So by this you have obtained a matrix like structure having 5 into 3, that is 50 elements, right? So this is the way how you have to find out the or complete this round array, okay. So let me summarize it. First of all, you have considered the elements of you have to write this coefficient, that is the polynomial of s to the power 4 to s to the power 0 in this column wise, right? So row wise, and s to the power 4, s to the power 3, s to the power 2, s to the power 1, s to the power 0. That will be one single column, and you have to find out the coefficient of this row is to containing s to the power 4 by given from the given polynomial. That means s to the power 4 coefficient 1, you have to skip one term, that means s to the power square term coefficient 18, next 5. Okay, similarly you have to form the array consisting of s to the power 3, that is 8, 16 and 0. See, 8, 16 and 0. Now the operation is performed with the help of next all the arrays or rows will be formed with the help of the two arrays already formed. Now how you have performed, I am given here first operation is actually shown by red line. That means this element is multiplied with the this element minus this element is multiplied this element divided by the first element. Similarly, to form the second element of this row, what you have done, this element multiplied by the next element of this row and minus this element multiplied by this row divided by the same element. So by this you have obtained the coefficient of, that is the this actually the values corresponding to the s square row. Similarly, you have to find out these elements of row s to the power containing s to the power 1. That means by the similar procedure you have to take the previous two rows and the same type of operations you are performing. Now we are not interested actually with the values so obtained, but according to Routh Hurwitz stability analysis criteria or Routh criteria, what it says is that sufficient and necessary conditions that you are not to be bothered about the element value. That means this is 1, this may be 0.5, this is 8, maybe 0.08, this is 16, maybe 160, whatever the values are. First of all, we have to do analysis whether the elements are having any sign changes or positive or negative sign, right? So let me discuss briefly what actually Routh stability criteria says. So keeping this array, I am removing all these sections. Okay, so you have to check whether all the elements of the first column of the Routh array, first you have to check. So this is a complete Routh array. You check, this is plus 1 plus 8 plus 16 plus 27/2 plus 5. Okay, so what you have seen, that all elements in the first column, only you have to consider the first column element are positive. Okay, so if Routh array, Routh stability criteria says that if all the elements of the first column are positive, if all the elements of the first column of the Routh array, that means I say if all the elements of the first column of Routh array are positive, then the system is stable. So according to this, the system I have considered, this is definitely stable system because there is no negative element in the first column of the Routh array. Okay, I will rewrite the only the first column elements and I will explain something. See, this was our characteristic equations. That means what does it mean? This is a fourth order system. Step by step, see what happens. If this is a fourth order system, first of all, there are 4 roots or poles. Definitely, there are 4 roots and poles, and this is your first column of the Routh array. And from the first column of the Routh array, what you see, all the elements are positive. So according to Routh stability analysis, it says that if all the elements of the first column of the completed Routh array are positive, the system is stable. System is stable. And if the system is stable, so from the generalized category or generalized rule, you know all the poles are on the left hand side of the S plane. Because in this situation, you see, we cannot solve these equations. One, you cannot solve it. Solve, not possible. So we cannot get the positions, right? Positions. We cannot get the positions. So if you cannot get the positions, so without this Routh array, you cannot get this part. That means this is not possible to find out the roots, locations on the S plane. If the positions is not possible to find out in the S plane, what does it mean? The stability cannot be analyzed. But by using the Routh array, what you have seen, if these all elements of the completed Routh array, first column elements are positive, system is stable. And in other words, if the system is stable, what happens? That means poles are on the left hand side, definitely. And how many poles are there actually in the system? 4 poles. And if all the poles are on the left hand side, so that means there are 4 poles on the left hand side. This is the conclusion. Okay, so comment on the system stability. If you are asked to comment on the system stability, what does it mean? It means that if all the elements you found from the Routh array is that are positive of this first column elements, then there are the system is absolutely stable. That means all the poles are lying, in other words, on the left hand side of this plane. If the poles are lying on the left hand side of this plane, system is stable. That means there are 4 poles, as this is having 4th order. So 4 number of poles or roots are lying on the left hand side of this plane. Okay, but you cannot get the positions. Maybe pole here, maybe pole here, maybe pole here, maybe pole here, whatever may be the pole, but they are lying on the left hand side. So exact pole locations cannot be found out by the Routh array, but stability idea can be obtained from the completed Routh array. Okay, so this is the case when all the elements are positive, that means system is stable. If so happens the system is unstable, then how can it be actually explained by using Routh array? That means if any sign, or you can say it, any negative elements present in the first column, very important, first column of Routh array, system is unstable. That means, for example, if 18, 8 and minus 16 was the case, if any case, I will consider one example. So where you will see there may be one or more negative elements in the first column. So if at least one element is negative in the first column, the system is unstable. And once the system is unstable, definitely there is certain number of poles on the right hand side. Unstable system means definitely there is at least one pole which is lying on the right hand side of this plane, right? So overall, Routh stability criteria says that from the completed Routh array, you have to find a check whether any element of the first column of Routh array is negative or not. If there is no negative elements, that means system is completely stable. That means all the poles are lying on the left hand side, first of all. If there is any negative element, system is unstable. And definitely there are certain number of poles which are lying on the right hand side. And system from the Routh array, it can be said what are the actual number of elements which are actually number of poles which are actually lying on the right hand side of the plane. In the next class, we will consider one example from where we can see the system can be unstable and how and what are the different numbers of poles lying on the right hand side of the plane. Okay, thank you.